should be recording now. Awesome. So let's jump straight in. So for question 1, it asks to find the final carbocation intermediate formed in this reaction. So one thing you want to be able to do is identify all the reactions that form carbocations. And so in carbocation reactions, that's where we see shift happens. So there's really only 3 reactions that you need to know that forms carbocations right now. So our first one, of course, is going to be our hydrohalogenation. And that's when we're adding things like HCl, HBr, H with any halogen, X I'm going to denote for halogen. Another reaction we see is acid catalyzed hydration. And then that's the example we see in question 1 over here. That's when we add water with H2SO4. And then lastly, we have acid catalyzed solvation. And this is very similar to when we have it with water, except this time, instead of having water, we have an alcohol of some sort. So it can be like methanol, ethanol, propanol. So I'm going to denote the alkyl group that's connected to the hydroxyl group. Sorry, let me let these people in. Okay. Yeah, I'm going to denote that just with an R. And of course, we have our acid. And so in each of these reactions,
recording in progress.
Sorry. You guys can mute yourselves, that would be great. But in each of these reactions, we see that we form a carbocation intermediate. And because this intermediate is planar, it has the potential to. And so there's 2 different types of shift we want to pay attention to. There's 1,2 hydride shift, where we're shifting hydrogen. And this one is always going to be preferred to a 1,2 methyl shift. But any shift that can make the carbocation more stable will happen. So in our first example, the water is going to have an extra hydrogen due to the acid catalyst. So it's going to be protonated, right? And so in our first reaction with all alkenes, the pi bond breaks, the nucleophile adds electrophile, which is the hydrogen. And so because this is going to be Markovnikov, we see that the hydrogen is going to add to our less substituted carbon over here. And so when I redraw this, I'm going to have a hydrogen on this side. This pi bond is going to go away, and then we're going to have a positive charge on our secondary carbon. So whenever we have this carbocation over here that forms, we need to check our adjacent carbon over here. So if our adjacent carbon is going to be more substituted than our carbon with the pre-existing positive charge, a shift is going to happen. So in this case, this carbon is quaternary. It has 4 carbon groups attached to it. So a methyl shift is going to happen. And we're going to see that this methyl group, along with these 2 pairs of electrons, are all going to get transferred over here. That way, we can produce a more stable carbocation intermediate. So let me redraw this. And in this case, we can see that we produce a tertiary carbocation. And that's going to be our answer to the first question. It's going to create a tertiary carbocation, which is much more stable than our original secondary. Okay. Moving on, and yeah, feel free if you guys have questions or anything, just feel free to interrupt me. So the rate determining step is whenever we break the pi bond. So it's going to be before the shift happens. All right. Okay. When we're dealing with Fischer structures, this was actually, I think, maybe on the 2021 test, but this was definitely on my exam in 2022, so you'll probably see this. whenever we're dealing with these sorts of like conversions, the first step is we always want to assign priority. We want to decide if our original structure that we're given is R or S, okay? So remember, we assign priority by looking at the atoms with the highest atomic number. If they have the same atomic number, then we look at atomic mass. And so first, right off the bat, we can tell that our bromine is going to get number 1 because it has the highest atomic number. Oxygen is obviously bigger than hydrogen or deuterium. And because hydrogen and deuterium, they have the same atomic number, we look at atomic mass. And we know that deuterium has an extra neutron, so it's going to be heavier than hydrogen, so 3 and 4. Now, when we're doing determining R and S, Dr. Berg likes to do the swap and flip method. Some people, they misuse this method. So I'll teach you the right way to do the swap and flip method, but personally, I like to do the rotation method. So when people are dealing with swap and flip, a lot of times they just go in and they say, okay, I have 1, 2, 3, I can just directly go like that. I'm gonna get an R, right? And then it's going to change into an S, right? So that's going to be incorrect, right? Because when we're doing the swap and flip, we want to make sure that the 2 groups that we swap, right, are going to be the ones with our lowest priority group and the one that's on the dashed line. Because essentially the idea behind the swap and flip is that we want to always make sure that our lowest priority group is on the dash rather than pointing toward us or on the plane of the page, right? So if we swap these 2 groups and then make this into 2, then we can rotate this way. And then as we know, this is going to be S, right? And so this would be S, and because we did do the swap, we have to change it to R because that's our actual one. And so, yes, this will be R. A much easier way that I like to approach it as is instead of doing all this crazy kind of swapping and going back and forth, instead, what I like to do is I just like to keep one of the groups constant and rotate the other 3 groups so that my last priority group is on the dash. So if I keep my bromine constant, and I'm just going to denote it with numbers because that's what actually really matters, and I change my lowest priority group and rotate it this way so that it's on the dash, and I rotate my OH over here, and then rotate my 3rd priority group over here, I'm going to get something like this. And again, this one does take a little bit more time, but you're guaranteed pretty much to always get the correct answer, even if it takes a little bit more time. Whereas the swap and flip method, if you go too fast or something, you might miss it. So I can go over here. And now we don't have to do any swapping or flipping. It's just directly what we see right over here. So we go 1, we go 2, and 3, and that's how we get R. Does everyone see how I do this method? Okay. And so now we want to redraw it as a Fisher structure. So remember, if the hydrogen or our lowest priority group is on a horizontal line, our R is going to change into an S, and the S is going to change into R. And the reason behind that is because the Fisher structure essentially has its vertical lines pointing away from us on the dash, and the horizontal lines are going to be pointing toward us. So if our lowest priority group is pointing toward us, then our parent stereochemistry that we assign needs to be switched because we always want our last priority group on the dash. So in this example, the easiest way I like to do it is I know that we have R, right? My hydrogen is going to be on a horizontal line and I want to make it into an S. So S is going to be counterclockwise. And so I just go ahead and do 1, 2, 3. That way you can do like just guess and check because there's only like a 50-50 chance, if you don't get it correct the first time, then you can just switch the 2 different atoms and get it correct the second time, but this is just like a way you can do it more systematically. So first group, we are there, OH over here, and D over here. And of course, there are other ways that you can draw this. You can also have it so the Br is over here, OH is over here, D, the hydrogen is over here, as long as it spins counterclockwise on the Fisher structure.
I have a quick question.
Yeah, go ahead.
So when you're doing that, like assigning the priority for the Fisher structure,
Yeah.
So can you explain that? Okay, so the first one we determined it was R configuration, but when we're writing it as a Fisher structure, it has to be an S configuration?
Yeah, because you're kind of like working backwards, right? So basically, with a Fisher structure, right, if I had the hydrogen on a vertical line, then I wouldn't have to do like the weird swapping and like doing like the apparent changes, right? But because my hydrogen is on a horizontal line, instead of doing R, I have to do S.
Yeah, I see what you're saying. Yep. Because for Fisher structures, when you're determining configuration, if it's on the wedge on the side, then you have to flip the configuration. Yeah.
Okay. Labeling alkene as E or Z. Okay, so looking at this alkene over here, whenever we're labeling anything as E or Z or deciding, for example, when we're naming something, whether or not something qualifies to be named as E or Z, we always want to check whether or not there are two different groups on like each side of the sp2 carbon. And what I mean by that is if I divide the alkene in half, am I able to differentiate between this group and this group in order to assign priority? And also, am I able to differentiate between this group and this group? So if A was the same as B, then I wouldn't be able to assign E or Z because there's no way to differentiate priority. In this example over here, we first see that we have our two sp2 carbons connected by a double bond with there. And if I divide this in half, I can tell that on this side of the carbon, for this carbon, I have two different groups over here. And so I also want to check my other side, and I see I have two groups that are different over here. And so I have to assign E or Z. If there was a case where I had the same groups over here, but these two groups were different, you would still need to use E and Z because you can assign priority that way. You only need to compare the groups on the one side that's attached to the sp2 carbon. Okay, so as far as actually determining priority, we want to remind ourselves that when we're given a carbon that's attached to an sp carbon or like carbon with like multiple bonds, like a double bond or a triple bond, each bond is like considered one attachment to that other atom. So so this carbon over here is attached. This carbon is attached to this carbon, and then this carbon is attached to three other carbons, right? So we first want to assess our first attachment over here. So that's just one carbon. And then we also see that this one is also attached to one carbon. Because they're both attached to carbons, we need to go a step further and find out what attachments are included in this carbon, right? So now I have to look at these bonds over here because these two are the same. So going a step further, we see that this one has three attachments to this other carbon over here. And then this carbon over here, you want to be careful. This is a skeletal structure. So I'm going to be attached to one carbon over here, and note that these are actually CH3s, right? But we're doing the nearest carbon attachment. So even if this had like a crazy chain, we're doing the nearest carbon, so that doesn't really matter. So one carbon, and then there's also going to be extra hydrogen here. Remember, each vertex with a carbon is going to have 4 bonds. So what's not labeled with another like carbon bond or another or no, like with another atom bond, is going to be a hydrogen bond to that carbon. So now we can tell this carbon is the same, this carbon is the same, but the carbon is bigger than a hydrogen. So I want to highlight this side, giving priority to this top group. Now let's assign priority to our other sp2 carbon. So as we can tell, these are both carbons, right? So now we have to go a step further and decide what these two carbons are attached to. So for this top group over here, I'm attached to one carbon, and then what's not shown is the extra hydrogen. So CCH. And the way I write it, I didn't write it as like CHC or HCC because I want to compare the highest priority first. That way I can designate if there are any differences. Okay. And then for this carbon over here, I have one carbon, and what's not shown is there's actually going to be a hydrogen over here. So this one will also be CCH. And so you're like, wow, they're both CCH. So now I have to go a step further, right? And so the next step we want to look at is, we know this side is attached to carbon, this side is attached to carbon. Where should I go? Should I go this way or should I go this way, right? Well, this way brings a bromine, and bromine is much larger than the methyl group over here, the carbon of the methyl group over there. So I want to go this way. This carbon over here is attached to a bromine and two hydrogens. It's not shown, but the other two bonds over here are going to be hydrogens. And then for this one, remember, skeletal structures are a little bit tricky. So there's actually going to be a carbon over here attached to two other hydrogens over here. So the way we want to look at it is one of the carbon attachments are going to be back to this carbon because it is a double bond. The other two attachments are going to be hydrogen, so CHH. And as we noted before, this bromine is much bigger than this carbon over here, so our priority group is going to be here. And then you guys probably learned a little way to remember, but I always go with like cis, or like cis, right? But we also talked about in like the review session, you have things like zine, whatever helps you remember. But this is going to be easy because they're both on the same side. If I had something on this side and this side, sorry, this side and this side, then it would be considered E. Okay, this question. So this question, we actually had like a variation of this one on a previous exam. So you might bring this degrees of unsaturation into this year's exam. We'll see. So I want to remind you guys that degrees of unsaturation can be calculated by the sum of the number of pi bonds plus the number of rings. There is like a more complex formula we'll learn later, but for this case, I feel like this is all you really need to know for degrees of unsaturation. One thing you do need to know is that oxygens do not change like degrees of unsaturation. And so the full formula, just so that you guys can understand it a little better, full formula for degrees of unsaturation is the number of carbons minus 1/2 the number of hydrogens minus 1/2 the number of halogens plus 1/2 the number of nitrogens plus 1. But in this case, we don't really need to know that. You can tell in this full equation that oxygen isn't really counted into it. So we know that when we write our molecular formula, we don't really need to count that. We just add it at the very end. Okay, so we see that we have one triple bond, 3 double bonds, and 2 rings. So one triple bond has 2 pi bonds, right? 3 double bonds, so each double bond has 1 pi bond, giving us a total of 3 degrees of unsaturation from there. And then each ring has a degree of unsaturation, so 2 rings give us 2. So 2 plus 3 plus 2 is going to give us a total degrees of unsaturation of 7. Okay, for the molecular formula, as we know, a completely saturated alkane, like a hydrocarbon, will have a formula of Cn, and is the number of carbons, H2n plus 2. And this will be an alkane, meaning you have no pi bonds, no rings, no double bonds, any of that kind of stuff. But when we do have a degree of unsaturation, we're going to do -2 times the degrees of unsaturation. And then we also know that this is just given in our problem. In this example, we have an oxygen. Oxygen doesn't really change the degrees of unsaturation, so we just snap it on at the end. All right, so we have 40 carbons. So for this formula, we're going to have 2 times 40 plus 2. And this is if it's like there are no pi bonds or rings, -2 times 7. And so this is going to give us C40H, so 82 minus 1468. This is going to be your final answer. All right, moving on, and feel free to stop me if you guys have any questions. There might be something on degrees of unsaturation, yes, because we did mention it in class. Might not be this complex with calculating molecular formula, but there was something similar to this on the previous exam, so it is kind of good. Okay, now let's give the product for this reaction. First thing you want to look at is looking at your reagents. So for your reagents in this case, we see that we have O3, -78 degrees Celsius, and this looks very much like an ozonolysis reaction. So what ozonolysis does is it cleaves this double bond over here, and it adds oxygens to these double bonds. So you can redraw it something like this to help you visualize it better, right? But another way you can draw it just to make it cleaner looking is your number. This is just for your reference, right? So I know it's going to be a 6-carbon compound. I can draw this. I know there's going to be a ketone on my carbon 2. And there's going to be an aldehyde over here. So this is equivalent to this, and if you draw either one, I'm pretty sure we'll accept it. Okay, ranking relative reactivities. So we briefly touched this in class, but this is something pretty important to know, and especially going on like later in test 3, this will definitely be heavily tested on. So it's really good that you guys get exposure to this right now. He does like to do ranking sorts of questions, as you guys probably saw on test 1. So let's get started. So when we're ranking relative reactivities, remember, if something is going to be less stable, it's going to be more reactive, right? And the opposite is true. If something is more stable, then it's going to be less reactive. So following like a schematic of things we need to like consider, right? The first thing we need to understand is our substituents, meaning what is connected. Yeah. So what is connected to my sp2 or sp carbon? Is it going to be an electron donating group, like an alkyl group? So alkyl groups, remember how we talked about the overlap that's due to hyperconjugation, right? That's just like electrons donating into it, making the bond more negative and making it more nucleophilic, right? So alkyl groups are going to be electron donating, and that just makes it more nucleophilic, right? And hence more reactive, versus something like a halogen, which is going to be electron withdrawing, and it's going to act more as like making it the pi bond of our alkene. It's going to make it more electrophilic and hence less reactive. Okay. The second thing we need to consider is alkenes are actually going to be more reactive than alkynes. So remember, alkynes, they have like shorter bonds, they have more S character, so they're more stable, versus alkenes are like a little bit bigger, longer bonds, right? So they're going to be more reactive in that way. And then lastly, we want to consider the substitution, right? Level of substitution. So in our case, mono substitute is going to be more reactive than di-substituted, which is more reactive than tri, which is more reactive than tetra substituted for alkenes. And why that is because mono is least stable because it only has, again, one alkyl group that's donating in electrons. And then di-substitute is going to be more stable, but it's going to be less reactive in that way, right? And so the same is true, like tetra is going to be like more stable, but least reactive. And mono is less stable, but most reactive. Okay, so now we can start. So first thing we want to check out is, okay, I can tell that all of them have like some sorts of like methyl groups, but this guy over here has a bromine, and bromine is an electron withdrawing group, which makes it the least stable, but also the least reactive, because in this case, remember the first thing we want to consider is that if it's electron withdrawing, it makes this alkene super like positively charged. Essentially, all the electrons get drawn over there, so it's not going to react very much. And this is in our like pyramid of different considerations, our number one. So this is going to be our least reactive. I'm kind of working backwards just so that the logic is more clear. And then next thing we want to consider is, okay, so we differentiate between our alkyl substituents and halogens, right? Next, alkenes versus alkynes. The only alkyne I see over here is this one. And I know that alkynes are going to be less reactive than my alkenes. So this is going to be number 4. And then lastly, I'm given 3 different types of alkenes, right? So my mono substituted is going to be my most reactive because it's the least stable. And then I have a cis di-substituted alkene over here and a trans di-substituted alkene over here. Because cis has that steric strain, it's going to be more reactive compared to the trans, where that steric strain is relieved. Okay. Moving on. All right, so I know the naming was definitely pretty hard. The naming would definitely not be this hard on the exam, but this is very comprehensive. So if you guys were able to get this, you guys will have like no trouble on the exam. I will say he won't do any like weird branches you guys probably saw like over here. He also maybe might not do like multiple like EZ or RS, but he might include things like Fisher structures. He might include things where it's like you have weird stereochemistries where like the priority 1 is on a dash instead. But everything else, I would say, you'll probably not make it as difficult. But given that if we're able to solve some of these, we're able to check all the boxes, and therefore it'll make us like better problem solvers on the actual exam. Right? So the first step that I always do when I approach naming is I want to find what my parent chain is and how many carbons, and then my functional group, right? So looking at this, I want my longest parent chain to include my alkenes and my alkynes. So, this has to be included. I also wanted to include my highest functional group. So my highest functional group over here is going to be my OH over here, and automatically if my OH is going to be my highest priority functional group, my amine is going to get demoted to branch status. So instead of it being like blah blah, like I don't know, 4-amine or something, it's going to be considered an amino, blah blah blah. Okay, so now I want to start numbering. So, oh yeah, so I want to start on the end of my highest functional group. And because I have an OH over here, which is closest to my right side end, I'm going to start numbering this way. Right. And then one thing I want to note before I get started on actually naming everything is I noticed that I have an alkene over here. So a lot of people, they like to name like E and Z or try to find E and Z naming like at the very end, but I like to like kind of start off with it because I know it's something I will miss. So right off the bat, I can tell that this is going to be like trans, right? So it's going to be E, and there's going to be like different groups on this side compared to this side, and then this side compared to that side because they're just hydrogen. So I'm just going to write a little E over here just to remind myself. And I know there aren't any like R and S because there's no like wedges and dashes, so I really can't determine that, right? So I'm going to start off with E. Okay, and then my branches coming off of it, I have a methyl over here, and a methyl group over here. I have another methyl over here. I have a methyl over here. I also have an amino group over here. And then everything else is either part of my parent chain or my alcohol, right? So I know that amino, the A comes before the methyl, so just start off with amino. And 4 trimethyl. Yeah, when you have multiple stereochemistries, you put them in parentheses, and it always goes in the order of the number that it's associated with. Does that help, Derek? Okay. And for trimethyl, and then I know my parent chain is going to be a nonane. I have a alkene. Yes, amino becomes a branch when there's alcohol because my alcohol is my highest priority. So the amino gets demoted to branch status. Yes. Remember, there can only be one bad boy in this. Can't be two. There's only one alpha. Okay. So I know that I have a nonane over here because I have 9 carbons, and then I have an alkene, so alkene comes before alkyne because the E in alkene comes before the Y, and this is just due to alphabetical, so non 6N. I'm gonna erase this. Okay, 6N, 8-ine, and then 2-O. And that's our name for our first one. Okay. Now looking at this Fisher structure, so sometimes I can get confused with like how many carbons are in a Fisher structure because it can get kind of confusing, especially with like naming things. So I just go ahead and just draw it as like a regular linear sort of structure, just so that I know, okay, I have like 4 carbons or 5 carbons. In this case, we have 4, so we know it's going to be a butane of some sort. I can highlight my expression. And we know that we have 2 stereocenters, right? So we're going to have to do the multiple stereochemistries where we put them into parentheses, right? But first, let me just number all my carbons. So if I go this way, right, I'll make the OH, which is our highest functional group, become a 3. But if I go this way, I'll make it become 2. So we're going to put them this way. 4. And then now I know that we're going to have a bute and 2. And then like some people, they like to start like naming just directly, like how I started with naming the branches. If you're comfortable with doing that, some people, they like building off parent chain is really what you're most comfortable with. For this case, I'm just gonna do it this way, but either way is fine. We also want to designate RNS. So remember how in the Fisher structure, we first assign priorities. So I'm going to assign 1, 2, and then remember there's a carbon over here and a carbon over here. So this carbon is attached to like the OH, the ethyl group, and the hydrogen, and obviously this one is going to be higher than my hydrogen. So 3, 4, and then I don't need to like switch it. In this case, because my lowest priority group is on a vertical line, which is pointing away from us, I got a dash. 1, 2, 3. This is going to be S. And then for this one over here, assign priority again, 1. So my second one is actually going to be this carbon over here. Remember, this is still carbon that's attached to like the bromine, chlorine, hydrogen. And because they're attached to these halogens, which are bigger in atomic number than this carbon with these hydrogens, right, that this carbon is attached to, it's going to be 2, this one will be 3, and then this one will be 4. And so I can see that my lowest priority group is on a horizontal line, so I'm going to have to reverse my stereochemistry once I look at my apparent one. Okay, so this is going to be 3. And that seems like it's S, but it's actually going to be R. So I know that the one with the OH is going to be R, and the one with the BR and the CL is going to be S. So right off the bat, I can just write 1S, 2R, and put that in parentheses with a little dash. Okay, now I want to finish off with all my branches, right? The only 2 branches I have in this case is the bromine over here and the chlorine, and they happen to both be connected to the first carbon. So going alphabetical, I know it's 1 bromo, 1 chloro, butane, 2. Moving on, let's tackle this monstrosity. So when we're given something that's cyclic and something that's a aliphatic carbon chain, meaning that there's no like ring structures, right? Determining which one is a parent chain, you have to determine, first of all, if it has any alkanes or alkynes and the other one doesn't, then automatically, because these have like specific functional groups that are making the parent have a higher priority, we want to prioritize that one first. So like first thing you want to consider is if one has more like pi bonds, right? Then it'll have like higher priority. and we would go with that. The second thing you want to consider is if they both have the same number. So for example, in this case, they both have one double bond, right? You want to go with the one that's the longer chain that has like more carbons. So if this group had like 5 carbons, then we would want to make this one the parent chain. But if this one had like more carbons, then that one's the parent. And then if they're equal, we always prefer to have the cyclic structure will trump the linear structure. Yeah, something like this could be on the exam. He might not do like a branch, but I'm trying to cover like all the different cases that he would do it. He probably, if he's nice, won't do something as complex as this, but this is just something you can have in your toolbox, right? Okay. Okay, so let's get started. First, we want to highlight a parent chain, so that's going to be our cyclobutane. And then we want to number. So I saw a lot of people make this mistake on the problem set, but a lot of people, they like numbering 1, 2, and 3 because 2 and 3 are like closest. But we actually have to number this. We actually have to number this, of course, like still through the sp2 hybridized like alkene, but we have to number it so that we give the substituents the lowest numbering priority, right? So something like this, if we numbered this as 1, 2, 3, 4, that gives us 2, 3, right? But if we numbered it the other way, where it's like 1, 2, 3, 4, even though we end on a 4, which it doesn't seem very nice, you always want to look for the first point of difference. And the first point of difference is our 1 over here. So anytime you have like 2 branches and then one of the branches on that sp2 carbon, and you don't have any functional groups, right? You got to note that this is like a sort of oxy sort of group, and then this is a chlorine, which they're both are branch status, so there's my priority. If you have like an alcohol, of course you want to prefer the alcohol, right? But if they're both branches, if a branch is connected to that sp2 carbon, it will always be number 1. Okay. So next thing I want to note is, okay, we can just go ahead and start naming our plants, right? So we know that this is a cyclo bute 1E. And in this case, the 1 is redundant. So if you don't want to include it, that's okay as well. And I know I have a chloral group, right? So 1 chloral group. And then I also have this huge group over here, right? So how do I name this? There's like a lot of things we need to consider, right? This is actually a branch. I'm just going to put this over here for now. But this is actually a branch. And so remember when we're doing branch naming, that the first thing we want to do is find out where it's connected to my parent chain. So in this case, my huge oxy group is connected to carbon number 4. So 4. And then this whole thing is going to be in parentheses, right? Because I have this. And then now I'm looking at this, and then I have 1, 2, 3, 4. I have 4 carbons. And the reason why I'm numbering this way as opposed to the other side is you want to number it so that the number that's connected to that oxygen is going to be the lowest. So in this case, it's going to be 2, right? So we know it's going to be a bute something in, and we know it's going to be connected to that 2 to il oxy. Okay. And I left a space here for the ene because we have to also designate where that alkene is located. So in this case, our alkene is located at carbon 2. Okay. And then lastly, we also, of course, as always, we want to consider if there's easy stereochemistry over here, right? This is probably something I should have done in the beginning, but again, like this just shows like how you kind of remind yourself because it's not something you want to like intuitively consider when you first start off, but it's really important that you do. And so when we're looking at this, we can tell that obviously this group over here has priority over here. And then we also know that on this side, compared to a carbon or an oxygen, my oxygen is going to have priority. So it's going to look something like a trans, which is the, so it's going to, and of course, we don't want to forget our one core. So that's a 4-ene, 1 chloro, 4 but 2-ene, 2-ill oxy, cyclobutene. Yes, it does contain stereochemistry, but it's going to be easy stereochemistry.
Can you please explain why, like the, you know how you have like the 1, 2, 3 written out, in terms of determining how you're gonna name it? Can you just run through that one more time, please?
Oh, just like the number, like the things you got to consider.
Yeah.
Yeah. So this thing is trying to consider where my parent chain is. So this is something you want to run through if like you have, let's say, a cyclic structure as also with a like an aliphatic like linear chain structure, right? So if you have both of those on the same compound, you're trying to decide where is going to be like my parent compound, right? And so the first thing you want to consider is whether or not you have like more pi bonds on one of them compared to the other. So if I had something where my linear structure had like more double bonds and then my cyclic structure was just like this, right? I would of course want to make my linear structure become my parent chain. So my parent chain would be looking something like that. And then my cyclic structure would just be like a cyclobutane, yeah, and then it will be considered as a branch, right? The second thing you want to, of course, if the opposite is true, then my cyclic structure is going to be my parent, and then my linear chain is going to be considered as a branch. And then the second thing we want to consider is that if they both have the same number of like double bonds or like triple bonds and everything, the one that has the longer chain is going to be your parent structure. So if you had something where like both of these, yeah, both of these, they have like one double bond, right? But my linear structure is much longer than this cyclobutanol. So I want to make my linear structure become my connection. Oh, the ill oxy. Yeah, okay, let me first finish this. And then the last thing I consider, like in this example, is if they both are like the same length and the same number of pi bonds, then the cyclic structure will always be the parent one compared to a linear structure. Does that make more sense?
Yeah.
Okay, cool. Yeah, so Jessica, yeah. The ill oxy, yeah. So it's kind of like when we have something like let's pretend we have some parent over here and then we have like an OCH3. Remember how we named this as like a methoxy, right? Right, that's kind of like how we do it. But because this is a branch, we have to include the ill with it, and then we just put the oxy at that. I don't need to note the ill oxy group in the parent cyclic chain as well. Connected to the oxygen. What do you mean by that? Both chains are attached to the oxygen. You don't, so this whole thing is a branch. Like, like this whole thing over here is considered one whole branch that's connected to this carbon over here. So it wouldn't be considered part of the parent. Why is the ill oxy not in the cyclic chain? Well, our cyclic chain is our parent chain, so we don't want to have the ill oxy. Are you talking about why we put it in parentheses and it's not just like all connected or something?
I think what he's trying to say is that you know how like you designated the one chloro for the parent chain,
Yes.
but like you didn't designate anything for the oxygen that directly branches off that. But
Yeah,
like I think yeah,
yeah, it should be this four over here. The four designates this.
Okay, so like I was saying, like why do you not write, for example, like why don't you write for L-oxy as well as like the L-oxy in the parentheses? Because like they're both it's connected to both chains. So like why wouldn't you write it on the inside and the outside of the parentheses?
Oh, so you're saying like you also write it on the outside, like ill oxy as well?
Yeah, like I don't get that part.
Yeah, yeah. So you only really need to write it once, right? Because like this whole thing is just trying to designate this one thing as like one compound. It's not like you have one like one that's inside of one. You know what I'm saying? It's like it exists as one whole thing by itself. So like this is a branch, right? Like this is a branch over here. But because it's just like connected to the oxygen that serves as like a whole oxy group, you don't need to include another oxy.
Okay, that makes sense.
Okay, okay.
Thank you.
Yeah, you're welcome. Okay. I will move on. And this is very similar. I think like the last example is probably much harder than this one. This one, you just have to pay attention to a lot of the stereochemistries. So right off the bat, I'm just going to designate these stereochemistries because they can be like in this, right? So first thing I notice is my priority one in this stereo center right over here, right, is on a dash, which means that my hydrogen is going to be on a wedge. Right? And so if I designate hydrogen as my lowest priority, this one is 2, and this one is 3. And then I rotate it so that my fourth priority group is on that dash there. I'm just going to rewrite this. I'm going to keep the 2 the same and then rotate it. Again, I'm like rotating so that this goes over here, the bromine comes over here, and then this methyl comes over here. Makes it much easier for me to name this. So this is going to be 1, 2, and 3, which is all. And then this is going to be R. And then this alkene over here, I noticed that it's going to be trans, right? So that's going to be E. And then this one over here, because there's 2 hydrogens over here, I know it's going to be cis, so it's going to be C. We also have a stereo center over here. My OH is priority 1. This alkene is priority 2. Remember, because this alkene is essentially carbon-carbon hydrogen versus this one is carbon-hydrogen hydrogen. So this is carbon-hydrogen. This is carbon-carbon hydrogen because of that double bond. So that's why this one has higher priority. This guy. And then we also have a hydrogen over here, which is our lowest priority, which is perfect because we don't have to redraw or anything. 1, 2, 3. And this is going to be S. Okay. So now that we see that we have all of our stereochemistries named, I'm gonna clean this up. Are you guys okay with me erasing some of this so we can write some more? Okay, perfect. Now, oh, why it's R? Okay. So the bromine, like the way I did it, I like to do like the rotation where I keep one of the groups constant, and then I like to rotate this one back over here, the bromine over here, and then this one over here. That just makes it easier for me to have lowest priority group on the dash and then have everything else on like a wedge or a line, right? And so by rotating it, I can see that this is clockwise, and that's why it's R. Another way you could do it, like I know Dr. Berg likes to do it, is that he likes to just do the swap and flip, meaning that if you move the hydrogen so that it's on the wedge and then switch that atom with that hydrogen group, and then go ahead and just find the stereochem, so it'd be 1, 2, and 3, right? It'd be S, and then just like switch it back to R because you do that swap. That's another way you can do it if you don't like to do the rotation method. Personally, I like it, but if that makes no sense. Okay, also, this is definitely going to be a pretty long review session. So if you guys need to go, this is will always be recorded. So just disclaimer. Okay, so now that we finished this, let me like clean this up. Okay. We want to find our longest parent chain. So in this case, if I look at this this like branch group, right? Like I know that, okay, because this one is also going to be some sort of weird branch, I want to compare which side is longer. So this side seems longer, right? Because this one has more carbons and this one has 3. So I'll go that way, designate my longest parent chain. And then I want to see where I can start numbering, right? So I want to start numbering so that my OH group gets the lowest number because my OH is my highest priority. So if I start numbering this way, 7, my OH is on 4. If I number purple this way, I can see that my OH is also on 4. Right, so now it really comes down to where I get my nearest alkene. So my alkene will serve as like a functional group that determines my numbering. And so in this case, I have 2 alkenes, so it's a diene, right? But because I get exposed to a alkene first over here versus this way, if I get exposed to an alkene on the second carbon, it's more preferable to have it at a lower number. So I'm going to go with my purple numbering scheme. Clean this up a little bit. So for this one, I know it's going to be a hept. And I know it's a hepta 1,5 diene because you always want to make sure that if you begin this with a constant, then you end this with a vowel. If you end this with a constant, then you got to begin this with a vowel. So I don't know. There's a way I can increase the resolution. Let's see. Does that make it look better? I don't know.
Yeah.
Oh, it does. Okay, okay, awesome. I don't know what I did. I just like removed the optimize for like video, but I'm glad that's better. Okay. Jared, I noticed in the key that the propoxy group has an ill in the name as well. If there is no methyl group, where do you include it? Are you talking about the branch? I'll get to it. Let's continue for now. Hepta 1,5 diene, and then I know that my OH is going to be ending it, so it's at 4. Oh, okay. And then now it's time for me to name my branch, right? So I know that it's connected to oxygen, and I can number it like this: 1, 2, 3. It's going to be a propan 1 ol. And then I know that this is going to be ending in oxy as well. Yeah, so there, I don't think there is a methyl group in it. Yeah, there's only going to be a bromo group in it, I guess. But the way we write the bromo is here. We just like move in, and then for the bromo group, because we have a stereo center that's inside of a branch, we need to designate that stereo center inside of the branch. Whereas like in these examples, like for example over here, we can just put the 1s and 2r on the outside. But because this is a stereo center that's inside of a branch, and there's going to be like multiple stereo centers on the outside, we have to put on the inside. So like in this case, right, we were able to put it on the outside because there's only one, right? But in this case, we have so many. So because we want to designate that this is part of the branch, we're actually going to put the 2R of the bromo on the inside. And then this is going to be our complete branch, right? That's located at carbon 1. And then lastly, when we were finished with all of our stereo centers, we don't need to worry about this guy anymore because it was part of our branch. Now we just go in the order of the stereochemistries of each of the locations. So this one I have a 1E. This one I have a 4S. And then this one I have a 5Z. And so our final compound is going to be 1E4S5Z 1-2R-bromo propan 1-il oxy hepta 1,5 diene 4-ol.
Hey, Jackie.
Yes.
So for that branch, the question I was really asking, I noticed in the top molecule, you designate the il as a number 2. But in this branch, there's not a CH3, like there's not a methyl group in the branch. So I was confused why the il was there. Wouldn't it just be propoxy?
So yes, you can write like propoxy and stuff like propyl oxy, right? You still need the il.
Why do you need the il?
Because
Is it because it's a branch?
Yeah, it's a branch.
Got it. Okay.
Okay. Is everyone good with all this nomenclature? Now let's do my favorite, chirality. Okay. Assigning configuration first. Okay. So as always, the first thing we do is we want to designate priority, like 1, 2, 3, 4. So we know that bromine is our biggest group. Our OH is our second. methyl third, and hydrogen will always be lowest priority. And again, you can do like the swapping foot method. I like to do rotation. So I usually keep one of my lines that are on the plane of the page constant. So in this case, I'm just going to choose the OH. And then I'm just going to write the numbers just to make it more simpler. And then, okay. And then for this one, I want to rotate it so that my lowest priority group is on the dash. And so we go here, and then method here, and over here, and so 4, 1, 3. Now I can easily go to here. And again, we can just bypass the 4. When we're like determining the directionality, we don't need to consider the fourth group, so this would be R. Okay, now for this one. This one, as I mentioned before, if the atoms have the same atomic number, then we go by atomic mass. So this is like an isotope of nitrogen. Nitrogen usually exists as nitrogen 14, but nitrogen 15 is just a heavier version of it. So this will be priority number 1. Number 2, and then we have these 2 carbon groups, right? As I mentioned before, each bond to that carbon is going to be like its own separate attachment to that carbon. So this is C, this is a CH, and so this one will be our priority number 3, and this one will be our priority number 4. And so again, we're going to have to rotate it so that our fourth priority group is on a dash. So in this group, I'm still going to keep 2 constants. I'm going to rotate it so that this one is here, 3 is over here, and then 1 is up here. Now I can sign. One, two, three, that, and so it's R. Okay. Now let's look at this fissure structure, very similar to what we saw before. Key thing to note that is in shorthand, right? Something like this is actually going to be carbon, double bond of oxygen, and OH. So in this case, something like this would be just CH. So because this one is connected to 2 oxygens, really it's actually going to be OOO because remember there's another double bond. This group is going to be priority 1, priority 1, priority 2, priority 3, and then priority 4. And we see that our lowest priority group is on a horizontal line, so we're going to have to reverse the apparent state. So if we go over here, that's S, and so we've got to change it to R. So R is going to be our final answer. And so a lot of these serotonin questions are pretty standard. I don't think they're like too challenging. I think they're very reflective of the actual test, so there should not have too much trouble with these. And I think like this one was actually maybe like on the column setters. So, okay. Again, we want to assign priority. So, for this center, we gotta remember that each intersection is actually a carbon that we need to consider, right? So if we look at the bottom one first, our bromine is going to be 1, chlorine 2, and then this carbon with all these attachments that's actually attached to this carbon is going to be 3, and our hydrogen is 4. So if we rotate 1, 2, 3, that's R, but remember our hydrogen is on a horizontal line. So, oh, I'm sorry, this is actually S. So it's going to be considered R. And then for this carbon over here, we see that that this carbon with attachments to all the halogens is going to be actually our first priority, right? Because compared to the ethyl group, which is attached to a carbon, hydrogen, hydrogen, and the methyl group, which is just hydrogen, 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 this carbon is attached to a bromine, chlorine, and hydrogen, which is much larger. So 1, 2, 3, and 4. And so we go like this, you can see that's R, but we know the hydrogens are horizontal, so we change it to S. Right. Moving on. So chirality and chirality. So with all of these structures, right, there's kind of like a schematic you want to follow. So for like basically for Newman projections, right? I'm gonna add a page actually. So I'm pretty sure there's gonna be 5. I mentioned this in the review session, right? But I would just like reiterate some of this again. So testing for like chirality, you'll be given like 5 different types of ways that a molecule can be drawn. You might be given a planar cyclohexane, a Hayward structure, and then in this case, you want to draw it as a planar cyclohexane. You might be given a chair conformation. And in this case, you also want to draw as a planar cyclohexane. And then you also might be given a Fisher structure. And then oh yeah, and then Newman projection. Newman projection, you always want to draw it as an eclipse conformation. And you want to do your best to try to have at least one group that is the same, aligned with each other. And what I mean by that is if you had something like this where you drew it as eclipsed, right? If you were able to align these groups together, you might have something like this, where you can tell that these two are not aligned, and thus it wouldn't be considered a meso compound, which is achiral. It would actually be chiral because these aren't aligned. But that's kind of what I mean by you want to have at least one of the groups aligned together. And of course, like Fisher structure, we also did a lot of examples with that, right? Most of the chirality things you can draw a plane of symmetry, right? The plane of symmetry is a pretty like fast way of determining whether or not something is chiral or achiral. So if there is one, right, if it's present, then the molecule is achiral. If it's not present though, then you want to go an extra step further, because sometimes even though it's not present, there might be a center of symmetry. And what I mean by that is if you were given a compound that was something like this, it would be very difficult to tell if this thing had like a plane of symmetry, right? Because if you cut it like in half like this, it's like very hard to tell, right? And then if you cut it like this, they're also not aligned, so it's kind of very difficult. So there's a foolproof method that I also talked about in the review session, right? So where you draw the enantiomer, And the essential idea behind this is you want to see if the mirror image of this compound is the exact same. If it's exactly the same, then the molecule is achiral. But if all the stereocenters are different, it means that this molecule has chirality. It's chiral. And one thing we want, this is called the mirror and flip method, right? Because we're going to pancake flip later, but sometimes it might be easier just to rotate the compound. So, so over here, the reason why we like to do the mirror and then we do a pancake flip is because pancake flip orients all the relative connectivities similar to each other, so it makes it easier for comparison. So if I were to pancake flip this, right, everything that was on a wedge becomes dash, but the connectivity, the parent connectivity, might appear to change, okay? And that's something you need to pay attention to when you're doing pancake flip. So for example, my fluorine over here is going to actually connect over here instead of connecting over here, right? So, and then it's going to change into a dash. My methyl group over here is going to change into dash over here. And then over here, this methyl group is going to mirror and attach over here, and it'll be a wedge. Essentially, all the stuff that's like down is now going to be up, and all the stuff that's up is now going to be down. This is very different from when you're doing the mirror image. And then, oh, sorry, this is going to be a wedge because again, my fluorine was on the dash before. And then now we have this molecule, and then once we're given this, we have to keep in mind that anytime you pancake flip, you have equivalent compounds, right? So pancake flip doesn't change it into enantiomers, doesn't change it into anything else. It's the same compound. And another thing you can do to make it easier on yourself to find whether or not this is chiral or achiral is you really want to heavily abuse rotation. So rotation is another tool that you can use to determine whether or not something is chiral or achiral. If I rotate this 180 degrees so that my methyl group over here is all the way over here without changing the relative upness, all the stereochemistries or anything, I'm just rotating the compound, I get something like this. So again, everything is rotated 180 degrees. And then now you can compare with our original compound, right? You compare this with this, and they're exactly the same. And this is what we call a center of symmetry. And this can make something achiral. Of course, if we see that, for example, in this compound over here, in this compound, in this case, you'll realize that after you do the mirror image, and the flip, you'll see
I have
that,
a quick question.
yeah, go ahead.
Yeah, so when you're doing the mirror and flip method, so like in like the first step in the mirror, you're essentially, for lack of better terms, you're flipping it in the vertical plane. That's what a mirror technically is, right?
Yeah, mirror is like flipping a vertical plane. In a pancake, you're gonna flip either vertical or horizontal, it doesn't matter.
Well, from what I understand, you're not really flipping it. You're just changing the stereochemistry, right? Or like the spatial arrangement of the molecules.
For pancake flipping,
I'm sorry, wait, did I read that wrong?
so mirror image, it's like kind of like, it's exactly what it seems like. Like if you hold up like a mirror to this, right? Like this is like still going to be like pointing towards it. This is also going to be pointing towards it. But with like pancake flipping, you're literally like swapping it like this. So anything that's like up becomes down. And then anything to the right goes to the left. Does that make more sense?
So it doesn't matter what plane the pancake flip is done in, horizontal or vertical.
Yeah, because the only reason why you want a pancake flip is to tell whether or not your mirror image is the same thing as your like original compound. So you can also use rotation as well. And then if it's the same as your compound, then you know it's achiral. But if it's different, like in this case, right, we can obviously tell, like the pancake flip is just to guide you and see that, oh, these relative connectivities are the same. Now I can compare the stereochemistries to each other. And I can see that these stereochemistries are like all different. So I know that this one has to be chiral. Because this mirror image is non-superimposable.
Okay.
Does it make sense? Okay. Yeah. And then of course, if it doesn't have it, no, then it's going to be chiral. Okay. So now let's go. So for the first compound over here, a lot of you guys might think, okay, so I know that I have an OH over here, OH over here, right? So this must be achiral, right? But we gotta take in mind that there are two possible stereocenters, right? We have one carbon that's over here, and then one back carbon. This round thing over here is the back carbon over here. And so although the front carbon is not chiral, our back carbon with 4 different attachments is going to be chiral because we have a methyl, a bromine, a chlorine, and then we have this huge like carbon with 2 hydroxyl groups. So this is going to be chiral. Okay, and then for this one, we know that we always want to draw it first as a planar cyclopentane in this case. And then if we do like the mirror and then swap method, and then we do a pancake flip. We can see that this is relatively down, this chlorine is relatively up, and that's opposite of this. And because each of the atoms are opposite, we know that these ones have to be enantiomers. They're not the same. So even though I drew the mirror image of them, like for achiral compounds, they might be the same, but for chiral compounds, they're going to be completely different. And so that's how I know that this compound is chiral.
So I have a question about this one. So how the so you said how for the first drawn cyclopentane structure, it's like you have the Br on the wedge and Cl on the chlorine on the first carbon, and on the third carbon it's the opposite essentially. But then on the once you do the planar flip, isn't it the exact same thing?
No, it's not the exact same thing because it's non-superimposable, right? Even if I were to like rotate this, right, it would look something like this, right? If I were to rotate this and then the BR was like up, right, because I want to like match it to this, and this CL was like down, right, and this CL was up, and then this one was like down, right? Even if I were to match it, you can tell that on the top over here, that's when you have like 2 carbons attached to it, whereas this one only has 1 carbon. So they're not superimposable.
Okay.
Yeah, the whole idea of the pancake flip is just to orient it so the relative connectivities are similar. That makes it easier for comparison. But like, that's just trying to compare the mirror images and seeing if it's exactly the same or different with the original compound. Okay, for this one, remember we can also draw like planes of symmetry through atoms and also through a double bond. But in this case, even if we drew like a plane of symmetry down here, this side has a double bond, this side doesn't. And then if we drew a plane of symmetry over here, it kind of might be difficult to tell whether or not it's going to be chiral, achiral, right? But we also know that this is going to be up while this one's going to be down, so it is going to be chiral. If you were to use like the mirror and flip method, this would be the mirror image of it. And then again, if you like did a pancake flip, the double bond will be on the opposite side. All the ups will go to down and all the downs will go to up. Sorry, it's a little crowded. But you can tell that these two chlorines are not the same and these two chlorines are not the same. So this is going to be a chiral compound. And you want like all your stereocenters to not be the same, and then that makes it a chiral compound because essentially the mirror image is non-superimposable. Okay, and then something like this where we have like a center of symmetry. I think I went over something similar like over here, right? So this is very similar to the example I went over before. So I'm not gonna go over it one more time because I feel like you guys probably already heard of it. Unless, do you guys want me to go over this one too? Okay, I think it's very similar to the ones I talked to before, so you can just take a look at that one again. And then also this one was like the exact same that I went over. So let's move on. Okay, so now we're looking at isomers, right? We'll definitely have like an isomer page, and this was like very reflective of the 2022 exam. So whenever you're given like two compounds that have stereocenters that are determined by an alkene, right? So like these stereocenters, they were determined by like sp3 carbons, right, with R and S, but these stereocenters are determined like cis or trans by the sp2 carbons. You'll never have enantiomers, so no enantiomers. No, because okay, yeah, Ben, for this compound, it's actually going to be chiral because if you were to draw like a line, diagonal line of symmetry, right? This fluorine is located over here, and if you were to have another up fluorine over here, then it would be considered as achiral. But instead, you have the fluorine over here, so that's not the same. Hopefully that makes more sense. And we also like went over the swapping flip method with this one over here. So we can tell that the mirror image, once I draw my mirror image over here, and then I do a pancake flip, right? We're gonna have this compound and each of the stereocenters are flipped, meaning that this mirror image is non-superimposable, meaning that it is chiral. Yeah, so if you have like stereocenters that are determined by the alkene, so this is not like RS or anything, then you'll never have enantiomers. The only two options you can have are either diastereomers, identical, or of course, like if like you find that they're different, it can also be different as well. So in this case, right, knowing what we said, you always want to abuse the ability to rotate compounds, right? A lot of people like, it's very underrated, like people don't really remember that they can do this, but you can rotate and then you can also pancake flip. So if I were to rotate this, where CH3 is like this. Remember that stereocenter is determined by sp2 carbons, or alkene are not enantiomers, so these are not enantiomers because once I pancake flip over this vertical plane, I get the exact same compound. So these two compounds will be considered as identical.
And you couldn't just like rotate it and get like, you know what I'm saying?
Yeah, I mean, like rotating this way too.
Yeah.
I think if you rotated it this way, right, you would have it like this, right? So you would need to pancake flip at one point, I guess. You need to pancake flip and then it would get something like this. Which will make it identical.
So here you mirrored. Did you mirror this one? I'm a little
No, this
confused.
one I didn't mirror at all. I just pancake flip. Remember, like, if you like these like stereocenters that are determined by like alkenes, they don't have like a mirror image, right? They're only like either cis or trans. So if I were to like rotate this, or even if I were to draw the mirror image, it would essentially just be a pancake flip. Right? If I were to draw a mirror image of this, it would just be like a pancake flip. There is no like mirror image associated with it. Yeah. Does that make sense?
Yeah.
Would you be able to show real quick what that would look like if it was a diastereomer instead of identical?
Yeah. So for a diastereomer, because this is technically like restrained on like 3 sides, right? So I can't really show it with this sort of structure, but if we had like an alkene that kind of looked like this, versus you were asked to compare it with something like this. You can see that like in this side, even though the connectivities are the same, right? So they're not constitutional isomers. This side is like, this is considered like a E sort of alkene, and then this is considered like a Z alkene. So these would be considered diastereomers.
Okay, thank you.
Moving on, whenever you're given Hayward structures, you always want to draw them as a planar cyclopentane in our case. So again, H2, H, H. And so again, as I mentioned before, you always want to see if there's a possibility that you can basically rotate them. So I want to rotate them so that their relative connectivities are the same, right? So that makes it easier for me to compare whether or not they're enantiomers, diastereomers, or the same, right? So if I rotate this one so that, again, this is just, this one is just this one, just writing it closer so it's easier for us to compare. If I were to rotate it so that this group was like rotated this way and then this group is rotated that way a little bit, so I'm not changing any of the wedges or dashes. Something like this, right? I can see, like, now it's pretty easy for me to compare, right? I can see that this fluorine is up, this fluorine is down, and then hydrogens follow opposite stereochemistry as well. And then this methyl group is up and this methyl group is down. So because both of them, or like all of the stereocenters, are reversed, I know that they're enantiomers. If one of them was the same and the other one was different, it would be considered diastereomers. And of course, if all of them are the same, they would be the same. So for enantiomers, you want to make sure that all of your stereocenters are opposites. Okay. Moving
Okay.
on. Okay. Again, for chair conformations, I want to draw them as a planar cyclohexane, and it really doesn't matter where you locate the different groups that are attached to the carbons, as long as they're like relatively located the same. So like, for example, in this case, I have a bromine attached to carbon 1, a bromine attached to carbon 2. I can put it here and here, or I can put it like here and here, whatever is fine. Just like make sure the number of carbons in between them is the same. If I had a bromine over here and a bromine over here, I want to make sure there's one carbon in between them. So in this case, I'm just going to draw this one up. And then this is equatorial up. Sorry, bromine and bromine. Now, in this case, sometimes it can be kind of tricky to tell, but if you drew like the axial counterpart to each of them, so for example, in this case, this is equatorial up, right? If I drew the axial counterpart, I know that that's down. So that means even if I had trouble determining whether or not this is equatorial up or down, I know the axial version is down, so the equatorial has to be the opposite, meaning it has to be up. So in this case, right, it can be difficult to determine, is this like equatorial up or is it equatorial down? Well, this vertex is like pointing this way, so my axial has to be that way, right? So because my axial is down, this one is actually up. And then this one, my vertex is pointing like this way, my equatorial is pointing that way. And because my vertex is pointing upward, my axial has to be up. So that means my equatorial has to be opposite, meaning it's down. So in this case, it would look something similar to up. And easily, if I rotate this a little bit to the side, right, I can tell that this one has a up and this one has a dash, which is down, and these have two ups. So because they differ at one stereocenter, they're going to be considered as diastereomers. So it's really important that for chair conformations, you guys draw them as a planar cyclohexane. For Fisher structures, the thing you have to keep in mind is that, first of all, plane of symmetries, they can go through like two carbons. So you can have a plane of symmetry like over here. In this case, it's not true, but like if you had another example, that would be true. Another thing you want to consider is that Fisher structures, you can never flip them. So unlike planar compounds where you can flip them, Fisher structures, they do show stereochemistry. Remember, the horizontal ones are wedges, the vertical ones are dashes, right? So if we actually flipped it, like pancake flipped it, it would change all of their stereochemistry. So you don't want to be doing that. However, you can rotate them 180 degrees, right? So if I were to rotate this 180 degrees, right now they look different, but my cue to tell me that I would need to rotate 180 degrees is that I noticed that this is like 2 CLs on this side and 2 CLs on this side, right? Also notice that this also has 2 CLs and this has 2. So if I can rotate them, then it might be that they could possibly be the same, right? So that's why I want to test it out. They both have like 2 methyl groups at the top, so that's pretty nice. And then I noticed that if I rotate it, Cl here, H here, Cl here, and then 2 H's over here. So essentially these 2 groups, they get rotated down there. And that's how I see that I have 2 Cl groups here, 1 Cl group here, so they're going to be considered as the same compounds. Moving on. And then
Yeah, it's not a question about this example in specific, but like, let's say that you have a Fisher structure or two Fisher structures. And I think Patrick mentioned that like if you determine the designation, the absolute configuration uh, for each bridgehead carbon, then like you could somewhat determine, or you could determine like whether they were diastereomers and enantiomers are the same. Would that procedure like work as well or no?
You can totally do that. I just did this because it's like faster and more visual, you know, so I kind of just like do this more by intuition. But if you do that, that's also perfectly fine as well. Yeah. Okay, and then for this one, I first of all, I want to notice where my attachments are. So I have a carbon here and a carbon over here. So I know this carbon is attached to a bromine and a methyl group, right? And then this carbon is attached to this alcohol group, the hydrogen and chlorine. And then I also have two carbon groups over here, right? So this carbon group in the front, I notice automatically that I have a methyl and an alcohol over here, whereas in this group, I have the methyl over here and the alcohol group over here. So they're attached to two different carbons on the Fisher structure versus in the Newman structure where they're actually attached to the same carbon. So these would be considered as constitutional isomers. And this is something you'll probably have to just remind yourself, like, so for like test one, it was like pretty easy to go through them as like finding the molecular formula and finding the relative attachments. But a lot of these, as you guys probably can see, you can just see them intuitively that you probably don't really need to consider things like molecular formula or like attachments because they already seem pretty similar, right? But especially for different structures that are drawn differently, learning how to find the different attachments is pretty important because they could be constitutional isomers. Okay, and then lastly, we have this. So again, you want to rotate one of the compounds so it's easier for you to compare. I'm gonna rotate this one over here just because I like the vertical orientation, the up and down over here because it's like easier to see, right? So I'm gonna rotate this just a little bit so that scoring is up over here. This one's over here, and then this one's over here. And so for this one, I noticed that for all of my stereocenters, they're different. So like this one's wedge dash, dash wedge, wedge dash. So like they're all different, meaning that they have to be enantiomers. Okay, moving on to the mechanism. So this is probably the most difficult mechanism that Dr. Burr might put on the exam. He'll definitely, he won't, so I'll make a list of what mechanisms you need to know. So you definitely need to know like the hydrohalogenation, all the ones that like form carbocations, right? So acid catalyzed, hydration, which is with the water, and solvation, which is with a solvent, right? These two you definitely need to know. He might ask about like how halogenation, which is like the example I'm about to show. It's like with Br2, or sometimes you guys know like we might have Br2 and then like H2O as well with it. But he won't ask anything about like hydrogenation, oxidation. He won't ask any of like the concerted reactions that creates like a pretty complex sort of transition state. He might ask you to draw the transition state that has come up in the exam before, but he won't ask you to draw like the full mechanism of it. So you might need to draw like the transition state maybe for like hydrogenation, where it's like something like this, where you form like this little square, right? So you might have to draw something like that, and it's very similar for hydrogenation oxidation, but no mechanism for those. Okay, so let's draw the mechanism. first thing that always happens, and it's always going to be your rate determining step, is the breaking of the pi bond and the addition of the electrophile. So let me draw this like this so it's easier. Okay. So your pi bond breaks and it adds electrophile. In this case, your Br2 is going to act as your electrophile, and as you know, like for things like with like water or like with a solvent, they're going to act as a nucleophile just because. Sorry, Derek, what was that transition state for again? Oh, the one that I just drew, that was for hydrogenation. So you know the H2 PD on C. But okay, so for in this case, you know that your Br2 is going to be your electrophile. And then basically if your solvent is present, it's going to be your nucleophile. And that's just because not particularly because it's like a better base. It is definitely a better base, but in our case, it's also because the compound is like swarmed with so much water, so much solvent. So it's definitely going to be more likely to act as a nucleophile. Whereas like with Br2, we're expected that it's like more limited, right? So in this case, Br is going to act as an electrophile. It's going to attack this carbon over here. And then this bromine is going to leave, right? So you're going to actually form an intermediate. So this is, again, your rate determining step. Your first step is always going to be rate determining step because that's when you break your pi bond. And then you end up forming this structure. The bromine has a former charge with +1, and then that bromine ion that left will have a -1 over there. And so now what's going to happen is your solvent or your like water or something is going to add to it. The whole thing is going to add. So even though at the end our product does not include a hydrogen over here, it's going to be part of a mechanism where we remove the hydrogen. In this step, the whole thing is going to add. So it's going to add to the more substituted carbon. And then this bromine is going to break off. So you're going to get something. And again, remember that oxygen with 3 bonds is going to have a positive charge. And the bromine is going to like this. Now, because we got to like remove the hydrogen from that positive charge oxygen doesn't like to have a positive charge, more solvent is present in the solution. And this is just like an assumption that you can make because, again, there's so much of it, right? That we can just use this as a base that removes the hydrogen and the electrons get turned back to the oxygen. Do you have to write arrows both ways? Yes. For all of these like steps and everything, you have to do equilibrium arrows. Okay.
Wait, that rule applies for the, you know, where you have your Br2 coming like with your original compound, that
Yeah.
like arrow towards the Br and then like towards that compound. So like those two arrows always have to be there.
Yeah. So like technically, like you're right, it favors more like this, right? It's probably like that, but it's always going to be equilibrium. Like all of these reactions are all equilibrium.
Well, no, I'm not talking about those arrows. Like the like in your first step before your rate determining step, you have the double bond that breaks and goes towards the Br.
Oh yeah.
Now you have to draw that second arrow that goes from Br to the double bond.
This one. Are you talking about that one? Like you have the pi bond that breaks, but then you also have another bond come here.
Yeah, I'm just curious if that arrow, that second one, you have to draw that.
Yes, because that's how it can create one bond to the Br here and another bond to that carbon over there. Otherwise, it would just be hanging off one of the carbons. Does that make sense?
Yep.
Okay, so, okay, and then this is going to be considered our proton transfer step, because again, this is acting like our base that removes the hydrogen. And so because this is only through a transfer of one proton, right, it's going to be considered our proton transfer. And then that's how you get our final. And again, also on the exam, make sure that you draw all of your lone pairs. And yeah, and for the mechanism specifically, you want to redraw like anything that you like reform for like the overall reactions. I know we don't really include the acid that gets regenerated, but because the mechanism, it's important to show that, oh, you reform what you originally had. It's important to like draw that. Okay, moving on. So this was actually a question in last year's exam as well.
Sorry, for the last one, when you draw that little extra thing, does it matter if it's like a plus sign with it, or can we just stick it in there?
Well, oh, sorry, there should be like another hydrogen over here. That makes it plus. Yeah, so like because like you want to like follow through with your last step, right? It's like basically this step takes another hydrogen over here, right? So you kind of want to follow through and then just show that it still has that proton.
Okay, so we don't need to put like a plus or anything or put it in brackets.
You don't put it in brackets, but you have to have the plus sign because that's just the formal charge of that oxygen.
Okay, sorry, I meant like a addition plus, not like a charge plus.
Yeah, you don't have to use that addition.
Okay. All right, thank you.
Okay, so for a reaction coordinate plane, you don't have to have actual numbers. You don't have to memorize any delta G's or anything like that. You want to draw just like the relative like ups, like the valleys and ridges, right? So of course, when we first start out, our reactants are over here. And then our highest energy state is going to be considered like that rate determining step, right? So this is going to be our highest energy. And then we're going to form our first intermediate. And so all of the humps that you form later on have to be less than your rate determining step because your rate determining step takes the most amount of energy. And so after that, we'll have the same number of valleys as the number of intermediates you have. So for example, if you form like a carbocation intermediate, only one intermediate forms in that case. So you'll only have like one little valley, right? But in our case, we have one, and then we have two intermediates that form before we form a product. So we're gonna actually have two valleys in our case before we form a product. And so in all OChem reactions, I would say it's safe to say that they're all exothermic because we're forming new bonds, right? Unless you stop in the middle of the reaction, let's say at an intermediate, or unless you have, unless you only break bonds and don't form any new bonds, then it will be considered endothermic. But this will always be exothermic. So the products, the relative amount of energy for the product should always be lower than the reactants. And so this kind of also answers this question. It has to be exothermic. And so I also want to, I like to differentiate like I1 versus I2, just say like they're two different intermediates, right? And then transition state 1, transition state 2, and transition state 3. Okay. And then, of course, like this will be the delta G. If it's not stated in the question, you don't have to label the delta G. I'm just showing you that G is less than 0, so it's exothermic. And then again, this will be like the rate determining step. Right? This is a delta G dagger for the rate determining step. Again, you don't need to show this. I'm just showing you where it's located. So for this specific reaction, the name of the intermediate that is formed after the rate determining step, it's going to be called a bromonium ion. And it was just something that we talked about in class. And examples of like considered reaction. So this example is actually not a considered reaction. The reason why is we form intermediates, right? Examples of considered reaction would be like hydrogenation, which is when you have the H2 beyond C, right? Anything that forms that little like square sort of intermediate, remember I was talking about, will be a concerted reaction. And then all concerted reactions will always be syn addition. So other examples are like hydrogenation oxidation. Another example is like epoxidation, which you do not need to know the mechanism for, but that's just another example of a concerted reaction. And we also know that epoxidation also adds syn. So all concerted reactions will add syn. And that's just because the time that the reaction takes place, it all takes place all at once. So it doesn't have the time to move around to the opposite side to add anti-addition. It all adds at once. Okay. We'll go over this extra credit question later at the end. I want to go through the reactions first, and then we'll do that ring expansion sort of. Okay. So he'll kind of like mention in the directions whether or not you need to give like multiple products or if you need to give enantiomers. Rarely does he ever ask for you to give all of the enantiomers. You only really need one, right, for full credit. But for like reactions that are stereoselective, for example, things that follow like Markovnikov's rule, where the hydrogen adds to less substitute carbon, stuff like that, you need to just show one reactant, one product, the most likely product. Things that give like constitutional isomers, for example, if you had like an asymmetrical alkyne and also an asymmetrical reagent, then you would want to show both products. So one thing, this was actually on, I think maybe group 12's problem set 6, right? Is if we add only one HBr, right, it's going to stop at the alkene because that's only one of the reagents that we have. But in the mechanism of this, and you'll find this in the textbook, right, what actually happens is that this alkyne creates a complex called a pi complex. And so it kind of looks something like this. And this is important to know because it changes the stereochemistry. Okay? It's not something we really talked about, but it's something that he might put, you know, just because he might not ask you about the theory behind it, but it's something that you need to know. And it's just that HBr or anything that are like two parts that make it stop at an alkene will add anti to it. And the reason why is because it forms this sort of like pi complex where something like this, right? Where it forms like this triangle. Remember, it kind of looks like our bromonium ion, and we know that bromination is an anti-addition reaction. Because it forms that intermediate, it blocks one of the sides that the other bromine adds to, right? So this works in a very similar fashion. So because that hydrogen like blocks one of the sides, the bromine has to add trans to it, and it's present trans in the alkene. So this would be perfect. So, and you do want to show stereochemistry with like cis and trans for this specific reaction. Okay. Okay, so now let's go through this. And the first thing I want to do is I always want to like classify like what is this sort of reaction? What does it add, right? So in this case, I know it adds H and Cl because it's a hydrohalgenation. And then next thing I want to think about is, does it shift? Like, does it form a carbon-cation? Does it shift? Oh, like Markovnikov or anti-Markovnikov. And then does it shift, right? And then lastly, I want to consider if it has like stereochemistry. And so stereochemistry only matters if it doesn't form a carbocation, right? And again, if it forms a carbocation, it has a possibility to shift, but it doesn't mean it will. And this is what this example is trying to show. So we know this acts Markovnikov. And these are just things you're going to have to memorize for each of the reactions. And you should know by now with all the practice you guys have been having already. So there could be a possibility. It could be, right? But it's not definitive. And stereochemistry does not matter. Okay. And so especially for these sorts of questions where you're forming a carbocation and stereochemistry doesn't matter, like I know in class we talked about how these reactions can form like a racemic mixture of like all the different stereoisomers and stuff like that. You don't need to show stereochemistry for the final compound for these ones that come from carbocations. So I know that my hydrogen in this case will add to the less substituted carbon, right? Pi bond breaks, adds the hydrogen, and the hydrogen is going to go to over here, right? And so I'll have a carbocation form over here. And so before my Cl adds, I want to see like, does it have the possibility to do shift, right? So first I want to classify this guy. So I know that this guy is going to be tertiary, right? Which is a very stable carbocation. So I don't expect any shift. I want to compare this one though. This one's quaternary. So you might think, okay, if that one's more substituted, right, is it possible that it might shift? Well, the thing is, a molecule is like a couch potato, right? It doesn't want to do shift or breaking or making any bonds if it doesn't have to, if it retains the same amount of substitution in carbocation and that. So even if I shifted, like I don't know what this is. Okay, sorry. If even if I shifted a methyl group over, right, I would make this one have a tertiary carbocation. So because both of them are going to be tertiary carbocations, the molecule is not going to waste energy and do a shift. So in this case, our final product will still have this quaternary carbon sort of situation over here. We'll have a hydrogen over here. And then the Cl will just add directly over here. Okay. Moving on. Again, in class, we also talked about two-step sort of reactions, where in the first step, you could have a specific reagent forming something. In the second step, you could have another reagent adding to that previous one. For these sorts of questions, we always want to see the final product. So we don't want to see like one, whatever product, two, whatever. We just want to see one product that comes at the very end. So for this one, sometimes it might be easier for you to first draw out the two different things that forms at each step, but you want to circle your answer that is ultimately the final product, right? So if just to demonstrate, for the first one, H2 luminous catalyst, we know that that is going to add two hydrogens, and they're going to add cis to each other. So I'm going to end up having something like this. This huge middle. And then the next question is asking, okay, so now we're going to be adding acid catalyzed solvation, right? Basically, we have an alcohol and also an acid. So again, in this step, there is, we can run through our checklist again, right? So what does it add? It adds an H and a methoxy group. Is it Markovnikov? Yep. So the hydrogen is going to add to less substitute, and the car is going to add to more substitute. Does it have the possibility of doing shift? Yep. And do we need to consider stereochemistry? No, because a carbocation does. So if my hydrogen adds to this one, right? Then I'm gonna have a carbocation form over here. And so now I need to think about like possibility of shift, right? So again, this is a secondary carbocation at the moment, and then this is a quaternary carbon, right? And so because this is more substituted, if I do a methyl shift, shifting this all the way over here, I'll have a carbocation on this side, and then now this will be considered tertiary. And so because a tertiary carbocation is more stable than a secondary carbocation, the shift is going to take place. And then my methoxy group over here is going to add to it. So ultimately, your final product is going to look like this. Okay. Moving on. So this is very similar to one of your problem set questions, right? It's similar to like the BR2, right? Where we do an anti-addition, right? And then we always want to make sure that in these cases, like in your, I think it was maybe problem set. Oh yeah, showing the last product. Are you talking about this one? Yeah. So for this question, right, because now we've talked about anti-addition and syn-addition, right, and we're given an alkene over here, you guys are expected to show stereochemistry for these ones. So we know that bromine is going to add anti to it, so again, like pi bond breaks in the less electronegative one. In other words, the bigger atom in our case. So this one's going to be more electropositive, and this one's going to be more electronegative, right? Is going to add to a less substituted carbon. So you're going to have and then because it is anti-addition, your chlorine is going to add on a wedge. And again, you can draw your iodine on a wedge, you can draw your chlorine on a dash in that case, but they both have to have like opposite stereochemistries because we are adding anti-addition. And then the other stereochemistry would just be the opposite of one of those. So I have the hydrogen left, and then also have a methyl group. Okay. So this question over here is really just testing to see if you know your reagents for your reactions. So just adding water, because water is a relatively like nerd sort of thing. It's not particularly acidic or basic. It's not going to directly add to the alkene at all. So no electrophilic addition reactions will happen without an acid catalyst with water. So in our case over here, this is an example of no reaction. So it's something you guys have to be careful about. Always look at your reagents. Okay, lastly, we have this thing, and we talked about this in class where we have something that's trans and an anti, right? And so we need to determine whether or not it's like erythro or thrio, right? So we have a little rhyme over here, which is like cis, syn, erythro. So if you change any of these two sorts of like categories over here, then the stereochemistry and stuff will still be like the statement will still be true. So for example, if I were to change this as trans, right, and then change this as anti, then my final product would be erythro. If I were to make it like if it was like a cis compound that was adding anti, right, then I would definitely need to still change this one to make it thrio, because remember, this compound holds true only if you change two at a time. Of course, if you don't change it at all, like cis and erythro, that still is true as well. Okay, so in our case, right, we just showed that it was trans and two, and so we know that final compound has to be erythro. And so you can just easily draw it as a Fisher structure. So we accept both like the wedge and dash structure or the Fisher structure. Just Fisher structure is much easier, right? So I'm just going to draw like a Fisher structure. On the answer key, you can see that I drew with wedges and dashes, but either is fine. With erythro, we know they're going to add on the same side. And we can just put our solution. For anything that's erythro, if you were to draw it as like anything erythro, right? If you're gonna draw it as like the dash and wedge, you just want to make sure that they are either RS or SR. That's like key to whatever's being erythro. Things that are 3O will always be either RR or SS. And erythro compounds have the possibility of being meso, meaning that they are achiral, right? And they have a plane of symmetry. So in this case, we do have a plane of symmetry. It goes through the middle like this. And so this would be considered like an achiral. That's just something you consider if they ask anything about meso compounds. Okay. So this is like a mini synthesis question. For test 3, I think it's going to be even more elaborate, but you guys have learned a lot of reactions right now that you're able to like piece together how they come, how they join up together to make new compounds. And so usually I first just like start with whatever is easiest for me. So I'll start with this compound right over here. It doesn't really matter which order you start with. I'll just start with this one. So I can tell that this is going to be like a trans alkene sort of situation. And so you might be like, oh my gosh, what is this? Like, this is crazy, right? What is this? Why does it have 3 oxygens? So this is actually our peroxy acid. So if you remember in like epoxidation, right, we use something called like MCPDA, which is like pretty similar to it, except it has like, don't like quote me for like making this absolutely correct, but it has something like this where it's like there's 3 oxygens, and that's essentially what a peroxy acid is. It has many different oxygens to create that sort of 3-membered ring, right? So with epoxidation and any sort of syn sorts of reactions, you're going to have stereochemistries that are written as cis to each other, comparing to like what you already have. Like what I mean by that is like you're not going to change to like being anti-addition. So let me draw this, that. So this time we do have a trans alkene. Sorry if I like that was a little bit confusing. I meant to say like they're all going to add cis. So like all the relative stereochemistries are going to stay the same. And so that's going to be your final product. And make sure you always draw them in pairs as well. Okay. So now this is a little bit complex, right? You're like, oh man, another like triple C, what is going on, right? So one thing you need to remember is sometimes Dr. Bird likes to throw like curve balls at you, right? But this is essentially the condensed formula for a triple bonded alkyne, right? And remember, if we have like an ion over here, like Na usually exists like this way, we're going to have the anion become like that. So this is a pretty good like nucleophile that we have, right? And so because Br is relatively considered like a weak nucleophile, right? It's like similar to our mechanism over here. right, where we have like Br2 serve as electrophile, this is going to be very similar in terms of how it adds. So this one is actually going to have like two different compounds, right, because of the way that our transalkene is substituted. So our transalkene, like this carbon over here, is like secondary, right? And this one's also secondary, so there isn't really like a preference for which one it adds. It's similar to how we have like an internal asymmetrical alkyne, right? So the Br can really add to this carbon over here, or it can add to this carbon over here. And so this whole thing will serve as your nucleophile, and it's going to add to the other one that the bromine doesn't add to. So if I were to draw this as a fissure, I usually like to keep my alkyl groups at the ends, right? And then I know that this is trans, right? So if I go by my little rhyme, cis and erythro, I know that if I change one of them to trans, and I know that this is an anti-addition because I have a Br2 that's adding, it's going to be anti, I'm going to have the erythro version of the compound. So that just means that my hydrogens are going to stay on the same side, and then one of them is going to be a bromine, and then one of them is going to be my nucleophile. And so the other way that this could add, again, these two are constitutional isomers, right? Is that the Br could add to this one over here, and then the triple bonded alkyne could add over here. And so you would need to show that these are two different constitutional isomers. Of course, like each one of these also has their own enantiomer, right? Because this is erythro and it's not meso, right? So it has another enantiomer, but you don't need to show it. And that would just be the mirror image of both of these. Now we're moving backwards. So now we see that we have like an alkyne over here. And the way that we can create a trans alkene is by dissolving, if you're dissolving metal reduction. So, and that's when we have sodium with ammonia at -70. Again, if we were to make a cis sort of alkene, then we would use H2 and the bars catalyst. And then lastly, over here, we see that we have a asymmetrical internal alkyne. Right, we have an internal asymmetrical alkyne. So if we were to add an OH and H, right, so they can add to either of these carbons. The OH can add over here, the hydrogen can add over here, or the OH can add over here and the hydrogen can add over here. And they would be two separate things because this side has a methyl group and this side has an ethyl group. So they would create two different constitutional isomers. And again, when we add an OH and H, if we're doing like acid catalyzed hydration, or if we're doing hydroboration oxidation, we always favor the ketone. We never write the enol version because the enol always tautomizes to the ketone. So what do I mean by that? So basically, first, when the OH and H add, let's say the OH adds to this one, okay? So I have my CH and then CH2, CH3. This is kind of like almost like an intermediate during the reaction, but because this is so unstable, it immediately tautomizes to a more stable form. So it actually formed the ketone. So like something like this. So the hydrogen that was originally bound to that oxygen is going to move to here. You have something. And that's one version, right? The other constitutional isomer would add the OH to this carbon over here. So you'll have this as your second product. Does anybody have any questions on this page? If not, I'll move to a very exciting ring expansion mechanism. So this mechanism we talked about in class, Dr. Berg did say that in previous years he did include this as like an extra credit something. So maybe he might include it this time, we'll see, but it's just pretty cool to do like by itself. This was actually a textbook question, so as you know, he always says that textbook questions are pretty fair game. Okay. So let's push this. First thing we always know that happens to any sort of alkene reaction is the pi bond breaks, adds electrophile. Now, thank you, Daniel. I'll continue like doing this extra credit question. If you guys like want to stay until the very end, that's fine. But this is all recorded, so if you guys need to go, that's still fine. Okay, so the pi bond breaks, right? And it adds electrophile. And then the electrons get returned back to the bromine. And so this is Markovnikov addition. So again, we add to the less substituted carbon, hydrogen adds there, and so we get a cation over here. Right. And so a ring expansion, right? Ring expansion only happens for things that are like cyclopropanes and cyclobutanes. Usually they never happen for cyclopentanes or cyclohexanes just because they don't have that bond angle strain. So like for these reactions, these molecules are like the number one priority is to remove that bond angle strain, right? So being able to do this ring expansion is very exothermic because it makes them more stable as a larger ring-membered sort of structure. So what happens in this case is this basically, this bond over here is going to associate with over here, right? So we're going to form a transition state. That looks something like this. Where this is your positive, partial positive. And the reason why I have like a partial positive on this carbon as well is because this bond is like dissolving. So you're essentially like losing a bond over there, right? Essentially, in this case, we do have an extra hydrogen. This one, you also have hydrogen, but because you're losing one of the bonds, this carbon is only going to have 3 bonds. It's like slowly starting to form that, right? And that's important because that's actually where our carbocation will be located once we finish the ring expansion. And so this is going to be our transition state. And then we're going to form something like this. I'm just going to draw like this so it makes a little bit more sense. So this will be a positive charge. And we have something like this. And this is equivalent to this. And so bromine can directly add, right? Bromine can add directly, but it's far more stable if we do a methyl shift, right? So because this is a secondary carbocation and this one's a quaternary carbocation, right? It's much more stable for bromine to be able to add to this carbon once it's done shifting. So if we do a shift, right, and again, all these arrows need to be equilibrium arrows. I'm just like too lazy to draw that, but yeah, they are all equilibrium arrows. We're gonna have a carbon cation over here. And so bromine can also add to this one. Right? And so if it adds to this one, which is actually less stable, it's gonna look like this, which is our first compound. And if it adds to there after finishing the shift, it's gonna look like that. And so as we know, because this is tertiary, right, this is going to be a more stable form. Awesome. Thank you guys so much for sticking around. It was a very long review session, but if you guys still have questions, I will end the review session first. So if you guys want to ask afterwards, that's fine.